Yes, suppose you want to find whether this kind of equation is correct or not, but now using dimensional analysis, and we are given that the position of x of a car at a rest at a time t, if the car starts from rest at x equals 0 and moves with a constant acceleration a, is given as x, which is distance, equals half at squared. That's the equation which we are given. X equals half at, x equals half at. Let me just correct this kind of equation. Yeah, so x equals half at squared. How do we check whether the equation is correct or not? So the principle of homogeneity, we are saying the dimensions in the left hand side should be equal to the dimensions in the right hand side. And in the left hand side, we are given x, and x from the statement, they are saying x is a position of a car. And if you are looking at a position of a car, you are looking at distance, where the car is. And we said in our introduction that any kind of distance, whether it's position, whether it's a length, any kind of length, the dimension of that particular kind of scenario, imakaraguti it's L. So in this case, x has the dimensions of L. So I put x in a square bracket of L. And also, we also given A. A is acceleration. And the acceleration, remember that acceleration is by formula, it's a distance divided by time squared. Distance divided by time squared. That's acceleration. So acceleration distance over time squared, time to the power 2. Distance over time squared. So if acceleration is distance over time squared, and we know that distance has dimensions of L. Distance has dimension of L, while time has dimension of T. So I put time as dimension of T. Therefore, the dimension for acceleration is L over T squared. Dimension of acceleration is L over T squared. We also said in class that you can also write this particular kind of scenario, L over T squared, in a straight line equation as L T to the power -2. That's what we said. LT to the power negative 2. So if you want to write the dimension of acceleration, you can write as LT to the power negative 2. Similarly, for the time, it's simple because we're already given time as t squared, so the dimension of time will be t to the power 2. That will be the dimension of time. Now, if you look at the left-hand side, if I write this equation in terms of dimension analysis, so the left-hand side, we have x, which is L, which has dimension of L. While on the right-hand side, we have the dimension of acceleration, which is here, times, so I put a dot, the dot means for times the dimensions of time, which is t to the power 2 as dimension of time. So this is an equation which we have derived from that particular kind of equation, x equals half at squared. Then we have as a dimension equation, the dimension of L equals dimension of LT to the power negative 2 times t to the power 2. If you look at this equation, you will see that we have disregarded 1 over 2. 1 over 2 is a dimensionless constant. And we said for all the constants, we disregard them when you are doing dimensional analysis. You just leave them. Unless you want to find a formula in which you can incorporate them at the end. But in our case, when solving for correctness of an equation, the dimensionless or the constants, they don't play any role. They are not important. Now, if you look at this particular kind of scenario, you'll see that you have only one dimension here, you have 2 dimensions, and you have 1 dimension here. As a rule, when you are dealing with the dimensions, it's very important that if you have a maximum of 2 dimensions, every dimension in the equation should also have 2 dimensions. And it's very easy to put 2 dimensions. From the knowledge of mathematics, we said any number raised to the power 0 gives us 1. And if you multiply 1 with any number, 1 doesn't change anything. The number becomes the same number. Meaning that what is missing from the left-hand side is only t. So you have L to the power 1. The 1 here is invisible. T, you can introduce a power of 0 for t to the power 0, meaning that t to the power 0 is 1, and 1 times L will give you the same L. Here we have already 2 dimensions. Here we don't have L. You can introduce L here, but when introducing L, you need to raise it to the power 0, so that L becomes a 1. This scenario is the same as the above scenario, because L to the power 0 is 1. 1 times t to the power 2 will give you the same t to the power 2. It's very important when you are dealing with the dimensions analysis, because you easily analyze each and every factor correctly. But if you just leave it others to have only 1 dimension, then others who have 2 dimensions may have problems in terms of analyzing your problem. Now, how do we go forward? We want to see whether this right hand side is the same as the left hand side. Left hand side will only have one variable, but the right hand side will have two variables which are multiplying each other. From the knowledge of mathematics, they say if you have the same bases and you are multiplying powers which have the same bases, what you do is you add the powers. So if you're multiplying L by L, multiplying L by L, you add the powers. Multiplying T by T, you add the powers. So if you're multiplying variables or numbers with the same base, they said we should add the powers. If you are dividing, you subtract the powers. And when a power is less to another power, they said you multiply the powers. So these are the basic rules in mathematics. Now here we are saying if you are multiplying, so I'll remove this bracket. If you are multiplying L by L, you maintain a base which is L, but the power we say you add. So L and the power of yan 1, but many the other L and the power of yan 0. So you add the powers as L t to the power 0. Similarly here, mukabanga multiply t uyu ndi t winai, the power mwambamu, you also have to add the power which is plus 2. So it's L so it's t to the power, we had a negative 2 here, which is negative 2 plus 2. Okay, so we have added this dimension. If we evaluate 1 plus 0, it will be only the power of 1. If you add negative 2 plus 2, what you have, it will be 0. So you see that the left hand side has Lt to the power 0, and the right hand side has L to the power 1t to the power 0. Similarly, here we said if you have Lt to the power 0, the L has a sided power of n, power of 1. And it's also the same as removing this 1 from here and just having only L t to the power 0. L t to the power 0. It's the same. Whether you put a power of 1 or you put a power of or you don't put a power of 1, the interpretation is the same. So if you look at the right hand side, you see that the right hand side is the same as the left hand side. And if the right hand side is the same as the left hand side, the equation it's homogeneous. And by dimension analysis, we can conclude that this particular kind of equation is a correct equation because all the dimensions are balancing. The dimension in the x right hand side is balancing with the dimension in the left hand side. So that's how we check whether an equation is a correct equation or it's not a correct equation. We also have another example. Let's say you're given an equation, and this equation is an equation of velocity. So you're given that final velocity is equal to initial velocity plus at plus at to the power 2. At to the power 2. That's an equation which we are given, and they are saying find out whether the equation is correct or not. Find out by dimension analysis whether the equation is correct or not. And if it is not correct, propose find the correct equation. Now, to find out whether this equation is correct or not, we use the same process here, dimension analysis. If you are looking at velocity by formula is given as distance over time. And we already saw acceleration, that acceleration is given as this velocity divided by time. Kavina good distance over time squared over time to the power 2. So these are the equations which we know. Now, to write this equation in terms of dimensions, we are given velocity. Velocity, we are saying is distance over time, which is L over t, or we say L t to the power negative 1. Remember this in class, L t to the power negative 1. That's final velocity. The initial velocity, the formula will not change. The formula will be the same, L t to the power negative 1 plus the acceleration. We discussed the dimension of acceleration as Lt to the power negative 2. Then we are multiplying with the dimensions for L to the power negative 2 times the dimensions for time is time, and it has dimensions of 2, L t to the power 2. So this is our dimension equation, which we have derived from that dimension formula. I hope it's simple now to find the dimensions. The dimension, you just have to know the equation, then you substitute. Now, if you analyze here, you see that this first part is equal to this first part, and an addition separates an equation, separates the variables in an equation, while multiplication merge the variables in an equation. So this dimension is equal to this dimension, but this dimension is not equal to this dimension. Let's analyze to find whether it's equal or not. If you look at the right hand side, if you are to evaluate the dimensions of time, they don't have L. And we said if somewhere the dimensions are not equal with the other dimensions in the equation, you introduce the missing dimension, but you raise it to the power 0. So by raising, we have the dimensions which are the same. Now, if you look at here, we have the same basis and are multiplying L to the power 1 times L to the power 0. So if these are multiplying, we said you add the powers. So we have a power of 1 here plus a 0 for the other variable. So 0. And for time, if these are multiplying, you add the power. So I have a power of 2 plus the 2. The other 2 is coming from here. If you evaluate this equation at the end, you have L to the power 1 plus 0, which is only 1. And this LT negative 2 plus 2, you find negative 2 plus 2 will give you a 0. So this will give a 0, a power of 0. So if you look, you see that we have L, and also have L. They're equal. But if you look at T, we have T to the power negative 1. We have T to the power negative 1. But here we have T to the power 0. Once the dimensions are not tallying, then the equation becomes an incorrect equation. So in this case, because the dimensions are not equal in the left hand side and the right hand side, the dimensions are not equal, then we say that the equation is not a correct equation by dimensional analysis. If the equation is not a correct equation, then you need to find the correct equation. That's what the question is saying. Find the correct equation. To find the correct equation, you look at the missing part. The first part is okay. It's okay to the left hand side, but the second part is not okay, meaning that V is not equal to V is not equal to V is not equal to A T squared. But V is equal to U. We have proved here that V is equal to U. But V is not equal to AT squared. So we need to find that part which is missing. To find a part which is missing, we write the equation of V, but we substitute where there is squared the power, because the power is what is giving us problems. AT to the power, we substitute the power with unknown, which we have to find. So I've just taken the unknown as n. That's what we want to find. So substitute the power with unknown, which we want to find. If you write the dimensions now, the dimensions will be the same as the dimensions here, but then the t will have the dimensions of unknown. The t will have the dimensions of unknown. Because that t is the part which is making the equation not correct. It's the whole part. The whole part here is the one which is making the equation to be an incorrect equation. So I've put the brackets for it is the whole part which we want to find, which we want to prove it to be a correct equation. So the dimensions for V we have already discussed. It's L t to the power negative 1, and this is equal to the dimensions of the right hand side. Let me put the brackets, square brackets. It's equal to the dimensions of the right hand side, which is acceleration, and acceleration is given as L t to the power negative 2. T to the power negative 2. And here we are multiplying with the time. Time, remember, is only t. And because it's only t, we need to include L, but this L should be raised to the power 0. L to the power 0, so that it should be, the dimension should be equal with the other dimensions in the equation. So we put a square bracket to close, but then this one is raised to the power n. All of that is raised to the power n. So now, first of all, to deal with this equation, there's a rule which says when a power is raised to another power, when a power is raised to another power, you multiply the powers. So I'll be quick. Lt to the power negative 1 as a dimension in the left hand side, and I'll evaluate the right hand side by multiplying first of all inside the bracket. I'll multiply inside the bracket. This L raised to the power L times L, and this L has a 1, it will be 1 plus 0, and 1 plus 0 give you just an L. So this L raised to the power 1 times L raised to the power 0. As a rule of multiplication, we said we add the powers, and here you have a power of 1 plus a power of 0, then 1 plus 0 give you a 1. So here you have a power of 1. So I'll put 1 for formality's sake. Then t is raised to the power negative 2, and because it's raised to the power negative 2, you add with the other t, which is raised to the power 1. So the other t is raised to the power 1, so I'm adding 1 here. Okay, and put a square bracket to the power n. To the power n. So if you add negative 1 plus 1, what you get here, it will be only negative 1. Okay, negative 2 plus 1, if you add, you'll be getting negative 1. L to the power L to the power 1, t to the power negative 2. Then you multiply the powers. Because you have a power of n here, you should multiply to evaluate the right hand side. T to the power negative 1 as a dimension equals the other side. If you multiply the powers, n times 1, you get L to the power n. That's the rule. When the powers are raised to another power, you multiply the powers. Then have t raised to the power negative 1. That negative 1 times n, you have negative n. Negative raised to the power negative n, raised to the power negative n. Now, okay, so a square bracket. So if you look at this this case, what it means is, if you take L, we said in an equation, the bases, if the bases are the same, the powers should also be the same. So if I just take L, it has the power of n. It means the power of L here is only 1. So this n should be equal to 1 here. Similarly, if I take negative n should be equal to the power of t, because t is less than the power negative n. Then negative n should be equal to the power of t, which is also negative 1. If you divide with the negative, you get n equals 1. So what it means is, in an equation, the equation which we had previously as a t to the power this number, okay, it means that n should be equal to 1. N should be equal to 1. So we have a t close bracket to the power 1, to the power 1. You can also write the equation as a separate, like v equals a to the power 1 t to the power 1, because a to the power 1 is same as a and t to the power 1 is same as t, then v equals at. Then our equation, the correct equation now, it will be this one. Here the power would not have a power of 2. We have only v equals uat, because at here, when you simplify it, it will give you lt to the power negative 1. We have already proved here that at gives you lt to the power negative 1. That's how you test whether the equation is correct or not, and also that's how you find a correct equation. You just have to make the left hand side equal to right hand side.